we want to call this a derivation, that the pressure is caused from two facts. Number one, how fast are they moving? Number two, their concentration. With a multiplication constant of R, we now have a mathematical connection between the pressure, the volume, the number of atoms, or I should say the number of moles of atoms, and the temperature. Now, of course, that doesn't quite answer the question about R. You could see R would equal to PV over NT. And so if you go into the laboratory and make some measurements, and so you take a container of a gas and you measure its pressure and you measure its volume and you measure its temperature and you measure how many moles you have, you will always get the same number. And so what you're going to be asked to do, and you guys will probably shoot me some questions because this is probably the hardest part of the homework this time, is that what would happen if I changed something? Let's say I increased the volume but left the temperature and the number of molecules the same. Well, that would mean the pressure would have to go down. Or what about this? What if I left the pressure the same but I increased the temperature, so temperature up, left the number of molecules the same? Well, that means the volume would have to go up. In fact, maybe I'll kind of show you that one. I should have showed you the other one. I'll go back and show you it to you. But the pressure on this little model here would remain the same because the pressure is determined by the weight of this little styrofoam. So if I took something like this, and the pressure is caused by the styrofoam here, I can then come over here and say, all right, well, what I have is I have a pressure that I'm not going to change. I'm just going to use the weight of that styrofoam. And the number of atoms here, the number of moles is the number of BBs in there. I'm not going to change that. But what I am going to do is I'm going to increase the temperature. I'm going to increase that by just turning up the knob, and what you will see is the volume goes up. And so sure enough, I come over here, I turn the knob. See, they go faster, but they also have more volume. Now the one I didn't show you, but maybe I should go back to, is what if I did this? What if I left the temperature and the number of atoms the same, but I increased the, well, the best way I can show it is by increasing the pressure. Then the volume would go down. And you can see that here. And so if I start at a high temperature, so maybe I'll put the knob up here, and then I do this, if I increase the pressure, the volume goes down. But the speed of them stays the same. And so that's this connection. And by the way, as a side note, for those of you who've gone through chemistry, this was first discovered by, not the whole thing, but the connection of pressure and volume with a constant temperature was connected by, or was discovered by Boyle. And so you've probably heard Boyle's law as you go through chemistry. That's kind of a common discussion. And so Boyle's law is a kind of a special case of the ideal gas law. So I'm trying to give you something bigger than just the Boyle's law that you might have learned in your chemistry class. And I guess another option here is we could do this. We could leave the volume alone and increase the temperature. And if I do that, the pressure will go up. And again, maybe you can kind of see this. If I maybe, to keep the volume constant, put this part way in so the styrofoam can't go any higher than that. And so turn it on, turn it up. All right. So then if I increase the temperature, turn it up, since my meter stick was blocking it, the volume couldn't go up. But as I turned the dial up, you might have heard it got loud. You couldn't feel it, but I could actually feel them hit harder and tried to push that thing up. And so they were giving me more pressure. And so I made the temperature go up, and then the pressure went up. And so that's the third combination I could have. And there's a lot of other combinations, but again, I better wrap up this chapter because you're going to have some neat homework problems that ask you to think about it. And this is the key, PV equals to nRT. And so you can change any one of these four, and another one or two or three would have to change to correspond to that change, because it's got to equal the same constant. It's got to equal this R. Now I got to say, the easiest problems, and the one we will do this semester, is we will leave two of them alone. We will change one of them and see what happens to the other one. And so we're usually just looking at two at a time. We're saying change this one and see how it has an effect on this one, leaving the other two alone. And that's what I was trying to show you. Well, as we come to the end, I need to give you this number. This number R is 8.31. When you measure pressure in pascals and you measure volume in cubic meters and you measure the number of atoms in units of moles, and absolutely important, you measure the temperature on the Kelvin scale. And so if you have a problem that doesn't give you those units, be very careful. First of all, the ideal gas law would only work if it's in the Kelvin scale. And so your author has deliberately, and you'll see it on the test too, deliberately given you a problem where the initial conditions are listed in Celsius. Do not do the calculations in Celsius, okay? Switch it to Kelvin. The author's trying to see if you're paying attention, okay? And I will do the same thing on the test. I will give you stuff in Celsius, okay? But make sure when you do your calculations, you convert it into Kelvin. All right, so that's the number. Now let me give you another number, because some of you have gone through chemistry, and chemists like to use this number, 0.0821. That is appropriate if you're going to use your pressure in atmospheres, which, okay, we will at times. And you do your volume in liters, okay, so we will at times. And then the number of atoms is still in moles, and the temperature scale has to be in Kelvin. So keep that in mind, because you kind of have both setups during your homework one. I'll give you even a better way. Here's what I like to do. I like to say, okay, I start off with some initial pressure and some initial volume with an initial number of molecules at an initial temperature that is equal to R. And then I do something with it. Maybe I change the volume, maybe I change the temperature, maybe both, maybe I change the temperature, maybe the number of atoms. But that new pressure, so I'll say final pressure, that final volume, that final number of molecules, and that final temperature must equal the same R. And so to make things a little easier on me, I just bypass R altogether. I don't care if I'm working with pascals and meters or if I'm working with atmospheres or liters. I like to just do this, that the initial pressure times the initial volume is then equal to the initial, or divided by the initial number of molecules over the initial temperature, is the same as the final pressure times the final volume over the final number of molecules over the final temperature. To me, that's the best way to do the homework problem. And so that's my hint towards you. And as you sit down and you read some of these problems, and they change things, like one of them has a container of helium that you're going to use to blow up balloons. And so the pressure is very high in the tank, and then you let it out and the pressure goes down. And so you have some initial pressure, and then it drops in pressure. And that means you're going to have some initial volume which then is going to increase in volume. Because then they also say that you're talking about the same gas, so you can conclude that the N over there is the same as there, so you can just cancel them off. They don't even tell you what it is, but you can cancel it off. And they also don't tell you the temperature, but they say you're blowing up the balloons in the room to have like a birthday party. And so the temperature of the tank and the temperature of the room is the same, and so you can just cancel off these bottom ones and you have the connection. And they do other problems like that where you can cancel off the volumes. But most of the time, in fact, I can't even think of a problem where they actually give you anything where the number of atoms change. And so those are probably going to cancel off right from the beginning. I'll put it up there in the equation so my equation is more complete. But to change the number of atoms is really more of a chemistry class than a physics class. And so we just cancel that off. We're not going to have a chemical reaction and change the number of atoms. Well, that's the end of the chapter, except for one more small thing. But I'll say it again. It took me a while to get here, and I apologize if I took too long, but I really like this chapter. Like I said, it's got a lot of really neat stuff here. In fact, a fun answer I love to give is way back. I don't know if you've ever heard the name Richard Feynman. Most people, when they ask, who is the greatest scientist of the 20th century? Everybody goes, oh, Einstein. True, true. And who's the second greatest scientist? And not everybody would agree, but most people, I think, say Richard Feynman. And so, although he's not really the most popular name, second always plays second fiddle to the number one. But Richard Feynman is brilliant, and he did some amazing work in the 40s. Ended up getting a Nobel Prize in '65 for all his work in the 40s. Passed away in the late 80s. He did the investigation of the space shuttle disaster in '81. But it was about that time, in about '81, and he was up there in age. And a reporter asked him one day, he said, "If we end up as humans wiping ourselves out due to an atomic blast or a pandemic, and only a few humans are left, what's the most important scientific information that could get passed on to the future generation so they can rebuild society?" And after he thought about it for a while, he said this, and I totally agree, that the most important information is that everything is made out of these little tiny atoms that jiggle around. And when you warm them up, they jiggle faster, and when you cool them down, they jiggle slower. Because that alone explains almost, not everything, but almost really the whole idea of physics. And that's why this chapter, to me, in the kinetic theory, is probably the most important thing we can do other than the 8 chapters before. Because as I said before, the chapters before really are the mechanics that you need to get through your next semester. And so for your immediate educational goals, those first 8 ones are the. But as for long-term knowledge and big picture knowledge, I think the ideal gas law is the big one here. And so I think took me a while to get here, but I think that's the most important thing. And I could go on and on about how many incredibly powerful and useful things that the atoms jiggle, and they jiggle faster with temperature, is an amazing statement. And so I like what Feynman said. I heard that years ago and just like, yes, that is totally, totally true. That is probably the most important piece of science. Now I'm sure not everybody would agree with that, just like not everybody would agree that he's the second best scientist or most important scientist, but that's how I rate him. Now, one more thing, and again, it has to do with this kinetic theory and the motion. It's called evaporating cooling. I believe that's how your author says. Yeah, he says, now keep in mind that as they jiggle around, if you have a container, say, of a liquid, maybe water, or I've got some isopropyl alcohol up here, but if you could imagine, here's the tabletop and here's a puddle of water, and this water or this alcohol is made out of a bunch of atoms and they're jiggling around. Some of them may be going fast and slow because remember, they're just randomly hitting. And so at room temperature, their average speed for these molecules in the air, maybe, and water molecules. The isopropyl ones are a little bit bigger molecule, but they have a speed of around 500 meters per second. And I told you earlier on in this lecture that they go really fast, and you might be surprised. And this is incredibly fast. This is 1,100 miles per hour. This is incredibly fast. And so that's roughly this average speed. But did you catch that I said average? See, the reason that's important is because like these BBs bouncing around, I'll show you again here. So they're all ricocheting around. If you look closely at them, some are going fast, some are going slow. It's a mess. And so when you talk about their speed, you can't say they're all going 500. You can only say on average. Which means some are going slower, but it also means some are going faster. In fact, some are going a lot faster. And here's the interesting thing. Some of them that are on the surface will get hit by maybe two at a time and go really fast, so fast that they actually get ejected away from the liquid. And now there's less molecules in the liquid. That's why we call it evaporation. You've probably seen a drop of water get smaller and smaller and smaller and smaller and smaller. Or a puddle of water gets smaller and smaller. It evaporates. After a rainy day, you get this little puddle of water on the sidewalk. And as the wind blows and as the sun shines, it eventually gets smaller and smaller and smaller. And eventually it's gone, because what's happening is those molecules are evaporating. But here's kind of the interesting thing. Which of the molecules evaporate? Yeah, the fast ones. The ones on the surface and the ones that are going fast. And so you can imagine if I had a classroom of students in here, and after the first test, some of them got high scores and some of them got low scores. And between the highs and the lows, there's an average. What would happen if all the students who got high scores left? What would happen to the average? You see, the average would go down, wouldn't it? And so when the fast ones leave, what you're left with is a bunch of molecules that now on average are going slower. Now remember, their temperature is their kinetic energy. Their temperature is that average. So if the fast ones evaporate, if the fast ones leave, the ones left behind are actually slower or colder. And so that's why the name is appropriate, evaporating cooling. Anytime the fast ones leave, the ones left behind are going to be a little colder. Now, water doesn't evaporate that quickly, but it does evaporate quickly enough. And so maybe you've noticed that a puddle of water is a little cooler. I brought out some isopropyl alcohol to show this to you. And so since this morning, this has been sitting out here since 8 o'clock this morning, so about for the last 4 hours or so, this has been sitting in the room. And so that piece or that container of alcohol has a temperature of, and so maybe I'll just kind of open up the lid and find out, okay, what roughly is the temperature of this isopropyl alcohol. And my thermometer here, well, I guess I'm getting the room temperature right now. It's kind of warm in here, 23.0. But let me get the alcohol temperature. The alcohol temperature is probably very close to that. Yeah, there it is, 22.4. But with a little bit of alcohol on the tip here, it is now hopefully evaporating. And look at the temperature now. It went down to 13.3. Because the fast ones left, leaving behind the slow ones. Oh, watch, I'll do it again. So I'll put it in here. So there it is, 22.4 degrees. I hold it up here. Maybe I'll even help it evaporate. But look at that, it's down to 12, or 13.5. It looks like it's all evaporating, and so now it's beginning to warm up. And I think you probably have felt this if you've ever, put a little bit of rubbing alcohol on your skin, or maybe you get a sore, or some aftershave that has the alcohol in it, and you put it on it, you could feel how cool it is. It's not that it was cold. I mean, it was a container that was in the room, and so you put on a little, isopropyl alcohol or a little bit of aftershave. I mean, you just got done shaving, and that's been sitting in there, and so the temperature of the bottle is the same as the room. It's not cold, but as soon as you put it on, it evaporates away. And of course, water does the same thing. In fact, this is how humans cool themselves. If I were to ask you, okay, how do humans cool yourself? You'd say, well, if I exercise, I sweat. Okay, so how does sweating cool yourself? Well, it's water. What? Okay, go on. Because if you say water's cold, I would say, no, the water came from inside of your body where it's warm. This is not the same as jumping into the ocean or a lake or a river where, okay, it's cold water and you cool down because you've jumped into the cold water. You're cooling down because it's evaporating. The water gets pushed to the surface of your skin through your pores, but once it gets on the surface of the skin, it's still warm water. What ultimately cools you then is the fast ones leaving behind cool water. And so that's how your body cools itself. And so humans have these things called sweat glands that allow water to come from inside of the body to the surface so they can evaporate and take advantage of this evaporating cooling. And that works great unless, and if you've ever been in an environment where it's humid means there's a lot of water already in the air, which means that as the water tries to evaporate, it can't. It's amazing how hot it can feel. Because if it's 90 degrees and you're in a desert, let's say you go to Las Vegas at 90 degrees, that doesn't seem so bad. Because what happens, as long as you keep drinking lots of water, your sweat glands bring the water to the surface, it evaporates off, keeping you cool, and as long as you have water inside you, you stay cool. But that same 90 degrees in Florida, I mean, you go to Miami at 90 degrees, and your body pumps the water up to the surface, and it doesn't evaporate, or it barely evaporates. And because of that, you feel miserable, and you feel much hotter. Yeah, it's still only 90 degrees, but your body has lost its cooling mechanism. And so a 90 degrees in a human environment does not feel the same to humans as 90 degrees in a dry environment. And so that dry heat, moist heat is a huge difference because it gets in the way of the way humans cool themselves. And that's why, sadly, you could read on the news, hey, it's 90 degrees in Miami, and they'll report a couple deaths. But 90 degrees in Las Vegas, no. And it's not that anybody didn't go outside or exercise, it's just that it's that mechanism of the way your body cooled itself. Well, there's more I could and probably should talk about, but I'll just say one more here along the lines, because you see this well with dogs. How do dogs cool themselves? See, dogs don't have sweat glands. They don't bring water to the surface. But they pant. And with nobody watching you, try a quick pant. You'll be amazed. Just kind of lay out your tongue and go. Now, not too long so you don't hypoventilate. But just that short thing, I could feel how cool it got on my tonsils and my throat. It's amazing how much water evaporated in that time. And that evaporation takes with it a lot of energy. And so again, humans can't pant, we hypoventilate, but dogs can, and that's how they do that. So again, dog needs lots of water. It needs its mouth open, it needs to pant, but it won't have any water on its fur. It doesn't sweat like you and I. Maybe I should say cats. Cats are a fun one. How do cats cool themselves? Yeah, and surprisingly, they pant too. The thing about cats, though, is they are either smart enough or dumb enough, I don't know what you want to say, I guess smart enough. They never do anything hard when it's hot. So they just lay around, sit in the shade, or stay inside if they have that option, and they never bother to pant. But they're still cooling themselves on their bronchial and their lungs by evaporating the moisture. And so their cooling mechanism is panting. In fact, you could even see some YouTube videos if you look at the lion. The lion is a good example where most of the time the lion on a hot day in Africa just lays under the tree. But once in a while, those pesky hyenas come into the pride territory. And so the king of the jungle there, he's got to get up from his lazy throne there, and he's got to get those hyenas off of there. And so in the heat of the day, he's out there chasing hyenas off and running around. And so when they're all gone and off the pride land, he'll come back and he'll just his tongue hangs out and it pants in a way that you don't normally see cats pant. Well, let's call that a quit to chapter 11. Good. We have probably 20, 30 minutes left in this lecture here. So at least let me start the next chapter here. Again, I went probably way too long on this, but I just really like this chapter, and I hope you do too here. And so let me just clear the board here and pull up my notes and say in the 20 minutes or so that we have left to work on this chapter, let's get started with chapter 12. And again, if you're looking at the syllabus, it says we're supposed to, start and finish chapter 12 today. We will at least start it, but we are behind here because of my long-windedness. And so we have a chapter to do. It's not a long chapter, but it's not a short one either. So we might catch up a little bit, but not completely catch up. And so I will begin here with what is chapter 12. And I would say chapter 12 is a continuation of 11. Remember, 11 is the structure of matter. And the next 3 chapters after that, although we're only going to do 2 of those 3, and so a total of 3 chapters on the structure of matter. And this one talks about the state of matter. Well, what do I mean by that? Well, why don't I just kind of explain? Because you might be familiar with the 4 states of matter. Maybe even the 5th state, but your author just talks about 4 of them and says the simplest one is what we call a solid. The next one is what we call a liquid. The next one is what we call a gas. And the 4th one we call a plasma. Although, let me put a little caveat here. The plasmas only exist for the elements and not the compounds. It's probably why on your early education, maybe middle school, you learned about these 3, the 3 states of matter. And you did not learn about the plasma. So I'll say a little bit more about the plasma. It's also why we probably have never heard of the Bose-Einstein condensation. Bose-Einstein condensation here. And so the 5th state of matter, maybe I'll just kind of throw it up there, but your book doesn't even mention or talk about it, and so I won't go any further on that one. But I do want to spend the little time we have left here in this lecture on what is a solid, what is a liquid, what is a gas, and then more importantly, what might be new to you, what is a plasma. So over here I've got some equipment to look at. Oh, maybe I better leave this up. I could use this. But the mental picture I want you to have of a solid is something like this. And really the best example I can give you is water, H2O. Because H2O you are the most familiar with. H2O is if you get H2O molecules cold enough, and in our case, put them in a freezer. And so if you take a container, put a little water, put it in the freezer, after a reasonable amount of time, they become a solid. And what we mean by that is they are hooked together. And so this is supposed to be my representation of a solid. That is, if I were to go to a freezer and pull out an ice cube out of the freezer, and if you kind of picture each round little circle here to be an H2O molecule, you would see that the H2O molecules are actually moving. So that's why we hook them with little springs between them. So they're moving around, but they are connected together. And so this H2O molecule, although it's moving, stays next to its neighbors. They're all hooked together. So that means if I took this solid and I threw it in the air, it would keep its same shape as I throw it in the air. They're hooked together. Now, if I warm it up, it'll start to shake. And the more I warm it, the more it shakes. And if I shake this more and more and more and more, eventually one will break off. Now, let me not get carried away and keep shaking this, but as I keep shaking it, as I warm it up, they will eventually break, and it'll stop looking like this and start to look like this. And so again, if you kind of picture this, each circle as an H2O molecule, and then what I would have after I warmed up this solid is I would get something that would kind of flow past each other. That is, the atoms would move around each other. They're not locked into place. Now, they're still what I might call quasi-hooked together. And so I might have something that looks like this. And if I put it in a container, its shape would be the shape of the container. It does not keep its shape. You know, I put an ice cube in a glass, the ice cube keeps its same shape. But when I melt the ice and I get a liquid, I get something that forms to the container. These different vases are really just curly pieces of glass. Illustrate it well. This is a big cylinder. This is a small cylinder or narrow cylinder. This one's got a little bulb in it. This one's got a corkscrew shape to it. But what I'm trying to point out is this liquid in here, and it's really just, I think it's water. Yeah, water with a little bit of food coloring, so it's red so it can stand out. You can see it better. But it takes the shape of the container. And so what I'm trying to then illustrate here is that the solid and the liquid are a little different. But where they are the same is they are still made out of H2O. Ice and water are each H2O. But they're in a different state. And that's this whole beginning part. This state is that they are hooked together. And when they're hooked together, we call it a solid. And that's the solid state. But this is what we call the liquid state. They're slightly broken. And then, watch this. You got to keep in mind that they're still shaking around because they have temperature. And what do you think would happen if I warmed them up? And warmed it up? And warmed it up? See how if I warmed it up so much they would break free from each other? They would completely separate. They would no longer be stuck in the container. They're free to go on their own way. They would look more like I've been showing you in the last chapter. They would look like this, what we're going to call a gas. If I turn this on, they bounce around. They're confined by their container, but they fill up the whole container. You see, a liquid doesn't fill the whole container. They're hooked together, so gravity pulls them down. But if you warm them up and they become a gas and they're free from each other, they will go up, and if the container's open, they will leave the container. If the container is closed, they will fill up the whole container. And so they're not hooked together at all. You might say that the gas is the complete separation that started way back in a solid where they were hooked together, and the liquid is kind of that intermediate location. And all of those are a nice way of saying, let me put it in words then, that a good way to define the solid is to say the atoms are held together so strongly that they will stay in their shape. Gravity will not pull it apart. You put it in a container, it doesn't matter the shape of the container, it still has its same shape. So an ice cube, when you put an ice cube in a piece of glass, the ice cube doesn't change its shape. It is still a cube. Now, once it warms up a little bit, the bonds begin to break. I like to say they break halfway, because they're not going to fully break until we get to the gas. But in the liquid state then, the atoms are still held together. So I'll put here held together. But not as strong. And so not strong enough to hold its shape anymore. And so that's why we like to say a good way to describe a liquid is you put a liquid, it'll go into the container and take whatever the shape is of the container. And so that's the important difference. And there's a lot of physics in this. And so hopefully you'll see that as we talk about a solid and a liquid, we'll begin, oh yeah, this is why a solid behaves different than a liquid. And it's all right here about how hard or how strong the atoms are held together and whether they would keep their shape or not. And of course, as I was trying to illustrate with my shaking of them, if you then warm it up even more, here I would say the atoms are no longer held together. The atoms are free to move on their own. They are not held together. And again, that has some interesting consequences in their behavior and the physics of it. So the behavior of a gas is different than a liquid. So just like the liquid is different than the solid, the gas is